So thank you everyone for joining us for our diverse webinar series. This is going to be the last webinar of the 2024-25 season. So stay tuned for more info on what we'll be doing in the fall. But before I introduce our speaker, I just want to start off with a land acknowledgement. The University of Alberta respectfully acknowledges that we are located on Treaty 6 territory, a traditional gathering place for diverse Indigenous peoples, including the Cree, Blackfoot, Métis, Nakota Sioux, Iroquois, Dene, Ojibwe, Saulteaux, Anishinaabe, Inuit, and many others whose histories, languages, and cultures continue to influence our vibrant community. So our speaker for today is Dr. Peter Osborne. He's a designer, architectural educator, and assistant professor of architecture, climate adaptation, and building rehabilitation at Carleton University. He was previously a PhD fellow at McGill University, and before that, a Knox Fellow at the Harvard Graduate School of Design. So with that, I'm going to let Peter take over, share his screen, and share about his work.
Awesome. Thank you so much for the introduction. Let me just get this going. Are you seeing my screen? Yeah. Perfect. Let me make it big. So hi everybody. Thanks for the invitation. I'm here to just chat about some of my dissertation research that I did during my PhD at McGill under the supervision of Michael Gemtrude, Kiel Mo, and yours truly, Christian Messier, who I believe just entered the group here. So that's really great to see everyone here. And thanks for coming by to listen to my chat. I'm going to try and talk for around 20 to 30 minutes, so we have a decent amount of time for conversation afterwards, because I think that's really what I'm looking for. So in general, what I'm here to speak about is this approach called the forest building approach, or forest building, a new approach to the integrated design of forests and buildings. Again, Catherine already introduced me. I'm assistant professor at Carleton University. Thanks a lot. So this talk will be in about 3 parts, and it'll be as fast as possible. So one is on the first article, which was published in 2023, called Forest Building and the Forest Building Traits Concept. The second is on assessing the resiliency of existing wood construction methods and approaches using kind of resiliency indicators developed in the ecological research industry, research academia. And then the third part is a land-based forest building biogenic carbon assessment, which kind of combines these 2 aspects together. So as I said, this article was published in collaboration with Nuria Akwile, Marco Mina, Kiel Mo, Michael Gemtrude, and Christian Messier in 2023. And this is a trait-based approach to both forestry and timber building and synchronized forest harvest and resilience. So I kind of came to this question about studying wood in architecture because this is what architects are told. So essentially, for every meter cubed of mass timber, we can sequester 417 kilograms of CO2 equivalent. But oftentimes, what's actually hidden behind this number and not available in most LCAs that architects are life cycle assessments and calculators that architects use is this kind of uncertainty. And essentially, the embodied carbon can also have a plus or minus of 657 kilograms of CO2 per meter cubed. So this essentially means that 1 cubic meter of mass timber can be sequestering or emitting carbon, and we don't really know as architects. So this kind of led me to understand the asterisks here is based on sustainable forestry management practices. So some of this stuff will be relatively simple for you ecologists and forest management researchers, but from an architect's perspective, this is rather novel to be entering into the world of ecology. So, this idea that forests are being utilized for anthropogenic needs is nothing new. Here I've adapted this from Christian's book, where essentially, forest management practices were used for protection from grazing and reforestation efforts. They were used for demands for glass, iron, mining industry, and agricultural production. And then in North America, they were dominantly used for timber for early age settlers. And more recently have been kind of changed to begin to support ecosystem services, ecosystem management, and now most recently in efforts to kind of adapt to the climate. So trying to decarbonize the construction industry, trying to use forests as the lungs to sequester as much carbon as possible. And this idea of using forests is nothing new. What I do question with is the kind of increased mechanization and increased demand of our timber and how that will be changed or how that will be influenced by ongoing changes in forest composition as well as climate change impacts on these services. So this is especially prevalent when you look at mass timber production and the kind of main driver of this increased wood utilization and construction as having almost a kind of a monospecies, and not only monospecies, but a very unique aspect of certain species utilization. So one example of this is Nordic Timber's mass timber products, or CLT products, use around 90% black spruce. That black spruce is not only black spruce, but it's a very specific form of black spruce that grows in about 180-year cycles, has around a 4-inch diameter, and is milled into kind of small lamellas that they're able to put together into a large kind of CLT panel, as you're seeing here on the left. And the concern about that is that kind of black spruce responds to only a single kind of functional characteristic, a single niche within the ecosystem, and may not have resiliency in many ecosystems, many regions of North America, especially in Canada, and could actually have changing composition, changing forest composition, which would impact their kind of future provisioning of that wood in the future. So architects essentially have many blind spots. So one of these blind spots that we often understand is we often don't see is the impact of fire. So here I've lectured many times in the US, and you're seeing an image on the right of the impact of the forest fires in 2023, where we found that, essentially that single season emitted double the amount of carbon of any forest fire of that year, and was close to the kind of national carbon emissions of all other industries combined. So it's quite a significant impact. So thinking about how our forests are changing and how that will, how kind of wood building and the provisioning of kind of a monospecies wood will impact provisioning, will impact the carbon resiliency of our forests is important. The second one is disease. Here, this may be a kind of prolific image that you all know, but many architects won't recognize that this is a historic image from the East Coast of the United States, representing the American chestnut. It's hard to believe that we used to have such large timbers on the East Coast, but only through the kind of disease American chestnut blight was this kind of decimated across all of Eastern North America, and something we don't see anymore. A further one we don't see is the impact of insects and pests on our forests. And this kind of starts to begin to hint at what we call kind of a forest building approach, where some of the beetle kill lumber is actually being harvested for kind of high value finishes. We're able to remove some of this timber from the forest and utilize it to then support forest regeneration efforts, et cetera, et cetera. And then not only are these things all kind of blind spots, but the kind of impact of climate change, the accelerating effect of indirect, direct, and interaction effects of climate change and all of these other kind of disturbance characteristics is massively impactful on our forest ecosystem structures. And in this article from 2017, Seidel et al. Concluded that ecosystems and society must be prepared for increasingly disrupted future of our forests. And this is something we really need to take into account from the construction industry. Finally, on top of that, the just massive amount of uncertainty that we have towards the kind of projected futures of our climate change will really impact the ongoing provisioning of wood, and something that builders and designers and engineers need to begin to think about a little bit more. So in general, what I'm looking to propose, or what I'm proposing here, is buildings tuned to the history and successional dynamics of forests and plantations. So buildings that understand, or builders and designers that understand how forests change and how they can kind of support that change, as opposed to one which applies a type of top-down approach that demands a certain type of wood from our forests. So just as ecologists have moved from species to functional traits and created new forests in the process, or you're creating new forests in the process, what I'm proposing here is buildings need to move from kind of building materials or building using certain species like SPF commercial groups to a building trait-based approach towards construction. And by doing this, we'll extend the ecological concept of plant functional traits to building. And what I mean by plant functional traits and building functional traits are extremely relevant. So from an ecological perspective, the functional traits, and I'm sure this is something you all possibly have deep knowledge of, could be things such as wood density, seed mass, height, specific leaf area, leaf nitrogen, drought tolerance, shade tolerance, and root depth. Whereas on the building side, they can be anything from the physical and mechanical properties, thermal properties such as emissivity and diffusivity, biodeterioration or rot resistance, fire resistance, and ability to be kind of suitable for wood preservative applications, bonding, finishing, etc. But what we found was when you look at the dominant species used to construction, so SPF species, spruce, pine, fir, mostly softwoods, they only respond to a very kind of to essentially two ecological niches in the region that we studied. And this is obviously because they're all softwood species dominant, particularly. So how can we begin to think about expanding our wood building practices such that we can support the utilization and the diversification of our forests in order to support their resilience overall? So the one way we tested this was to apply this kind of approach on the Centre du Québec region. We leveraged the study by Marco Mina et al. From 2022. Where they looked at different forest management approaches and climate change impacts on increasing the resiliency of the region. And they had never studied the harvest output. So we leveraged the harvest output data for that study to assess the social and ecological impact of climate change and forest management change on this region. So you see here on the right the kind of array of scenarios that we looked at, where you're seeing different climate change scenarios for here, current climate, RCP 4.5, and then the RCP 8.5 climate change scenario. So increasing climate change impact from left to right. And then from top to bottom, you're seeing business as usual forest management approaches, climate change adaptation forest management approach, and then the functional diversification approach of two different intensities, essentially a medium intensity and then a higher level intensity. So we were able to assess the impact essentially of time on forest harvest output, of climate on forest harvest output, and then different kind of management approaches on forest harvest output. And what we found was that when forests were of low functional diversity, the kind of dominant species that could be utilized were typically when the forest management was business as usual, we had relatively low functional diversity of wood utilization. So we were dominantly needing to use building groups 1 and 2 still, whereas we still had significant amounts of BG4, which is typically hardwoods, maples, and a few others. But as we increased to the highly functional diverse forests and high climate change, we actually found that we drastically increased the harvested output of both the kind of standard SPF commercial group species, so building groups 1 and 2, but also building groups 4 and 5 substantially increased. And what this allows us to do is to really understand when, with what species, and how to build with wood. And finding value. And what this really pointed towards is the need to really find value in unutilized wood species. So you're seeing here on the right in this chart, as essentially the forest becomes more functionally diverse, and here in the bottom right, we didn't find necessarily that we increased substantially the SPF species, as those weren't the ones that were needed in the region. But what did actually end up happening was over the course of the entire 170 or 190 year study period, we dramatically increased the harvested output of building groups 4 and 5, which kind of points towards the need to find value and find utilization for those wood products in long-lived carbon stores such as buildings. So moving to the kind of second part of this study, we looked at, this is the kind of a forthcoming article called Wood in Transition, Diversifying Wood Construction to Cope with Forest Change. We looked at ecological indicators of resiliency. So the three of them we identified were species richness, functional diversity, and functional redundancy. So species richness is obvious, essentially the number of species that essentially can be attributed to each product. So when you begin to assess this, you can look at how products like dimensional lumber of commercial group SPF have 4 species which they can utilize. Whereas when you begin to increase it to kind of all the different commercial groups, you can kind of aggregate them together and they get substantially more species are able to be utilized in them. And then comparing that to a product such as plywood, we found there was, 17 different species available within the kind of plywood market. And that makes that product a slightly more resilient product to change as they're able to adapt their systems. And then finally, when you kind of aggregate these things together into a construction, we're able to even find more benefits where, the SPF species and then the plywood together kind of provide kind of a unique combination. Where this becomes particularly interesting is when we begin to look at these other kind of ecological indicators of functional diversity and functional redundancy. I'm not going to kind of go too far into the depth of this, because I think Christian has probably introduced it and many people here know the concept in general. But essentially what you want is, for a highly functional diverse forest, is you want species which have ecological traits that are varied in their response to different disturbance characteristics. And you similarly want highly redundant forests, which have kind of functional overlaps between their species as well. So when you begin to look at kind of the wood product characterization according to their functional resiliency and functional redundancy, we find that products such as mass timber, which are a single species, typically have extremely low functional redundancy and functional resiliency, as they only have one species typically that they're using, possibly one or two. This chart here is only using a single species approach here. Whereas products such as dimensional lumber, which often use significantly overlapping species, so many softwoods, but have a high functional redundancy but a low functional diversity. And then comparing that wood panels such as plywood, OSB, LSL, and those varied products which can utilize a higher variety of wood species, begin to develop into a much more highly functional diverse approach. And in combining these approaches together, or combining these products together through light frame construction using all commercial groups, and through timber frame and or kind of this mixed adaptive approach, which utilizes timber frame, light wood, wood panels, etc., are we able to actually have a highly functionally redundant and highly functionally diverse forest. So you can begin to understand how the kind of forest management approaches that we're proposing, so highly functional redundant, highly functional diverse forests, would be best supported by an adaptive approach which is able to use the most species, whereas a mass timber product would possibly align itself best with a very simplified forest. It's quite a simple concept, but depending on the direction you're going here, if this is a demand or a supply side approach, that really has an impact on how we're working with our forests and our buildings. When we begin to think about this further and assess the kind of harvest resource availability of the region, this question becomes particularly interesting. So you see here on the right, essentially how the timber frame mixed species and light frame commercial using all groups significantly increases as the forest composition becomes essentially functionally more diverse. And whereas the kind of light frame mass timber and mass timber black spruce really suffer in the later years of the simulations. And kind of furthermore, when you begin to incorporate the kind of efficiency of wood utilization for each of these products or each of these approaches, where light frame is kind of the baseline of 100% utilization, mass timber uses around 550% more timber per unit volume of live space, and kind of the timber frame adaptive approach uses around 245% more timber. So it kind of begins to flip it on its head, where suddenly the all commercial group light frame becomes the most supportive for the Centre de Quebec region, and the kind of timber frame mixed species becomes the second. But what's particularly interesting about these kind of tables and these charts is that you can see how in the timber frame mixed species, the line is relatively flat, which shows something about the kind of impact that will have on the industry in general, showing that, as climate change moves forward, as these disturbances occur, the industry is able to shift and adjust itself in order to maintain kind of consistent supply. Whereas if you're looking at the kind of light frame approaches, they are impacted quite considerably depending on the different kind of climate change scenario that we're looking at. So finally, I want to talk about kind of the carbon impact, because that's really where this question began. So this kind of second forthcoming article that I'm writing in collaboration with the Canadian Forest Service on enhancing forest carbon sinks through functionally adaptive wood construction. Will be coming out hopefully this year. But my question here is really, what is the impact of a functionally adaptive building practice on the land-based carbon pooling potential of buildings? So again, we utilize the same study region, and we really wanted to understand how much carbon can be stored in the kind of wood-based carbon pool of this forest region. So we developed a species-level forest carbon model using the Harbor Products model developed by Canadian Forest Service called ANSI, which I'm sure if you have experience with, where we looked at essentially everything after the forest. Further studies, I'm hoping to actually include the forest carbon into this, because I think that's a really critical element, but this is the kind of system value that we're looking at. So everything from the kind of production to the use in building and then its eventual end of life. And what became really evident when you looked at the utilization rate by each scenario for this region, especially, is that mass timber was just not at all suitable. There wasn't enough of the species that was utilized in it. Whereas when you look at light frame and the kind of adaptive approach, we're reaching something around 40% for light frame and upwards of 80% utilization for the adaptive approach. Become particularly interesting too when you look at the changes between the kind of low functional diverse forest and the high functionally diverse forest, where you're seeing kind of a pretty considerable increase in wood species utilization. So the diversity of wood species, which was evident in the last paper that was discussed, but as well as the significant quantity differences and changes over time or between the two scenarios. So I don't want to go too much detail because this is kind of a bit dense, and I would rather get to questions. But essentially, these two different kind of charts are showing the usable wood over time and the total wood in the built environment between the kind of current and the extreme scenarios. So what you see here is essentially the current scenario having a much more limited supply, not limited, less diverse forest. Whereas you move into the kind of adaptive one, you're seeing just a much more kind of diverse forest and therefore a much more diverse building. So what's important to think here is that how does the building's kind of fingerprints match on to the kind of forest output that we're seeing? And then finally, the other element of this is that we really wanted to jump into is the actual kind of byproducts that are coming out of these different approaches. And one of the really important aspects of this is the percentage of utilizable wood within each of these approaches. So softwood species are often have around 80% utilization, whereas hardwood is more around 45. This is a broad generalization, and I'd love to get into conversation about more specifics on this with the group. But when you think about this in terms of the kind of co-products and byproducts as well, moving down the supply chain, you find that essentially each kind of wood product has various efficiencies or a varied efficiency in its translation from forest to built environment. So lumber, for example, has around 43% of the actual biomass from the tree. In forest is actually maintained in the wood product, whereas things like OSB or in strand board, which can utilize kind of essentially chips and a much more whole volume of the tree, gets above 75% utilization. So it's really important to kind of consider this when evaluating the impact on the kind of total carbon pool, because the end life of these byproducts is something that's really critical to think about as well. So to conclude, essentially when you're kind of combining these things all together, we find that we're able to increase the essentially wood-based carbon pool by going to a more functionally adaptive and functionally resilient forestry and building practice by between 105 and 295% wood utilization. So where that's really important to think about is with respect to both where we're going to put those and how we're going to put those into our built environment. So what types of buildings are we going to be producing with those? Are they light frame buildings? Are they the timber frame adaptive buildings? Are they plywood? Are they OSB? Because I think that really is impactful on the eventual kind of co-product and byproduct outputs of these different approaches. So where this becomes really interesting is when you think about kind of this whole system together and how we need to begin to think of, if we're going to diversify our forests, how we need to be able to think about the impact this will have on industry, the impact this will have on the increasing co-products and where those co-products are going to be going, whether that's into other long-lived products or whether that's into short-lived products. And this is something that we're hoping to essentially continue to study over time. So essentially, what this kind of approach is able to do is capture the integrated complexity of forest building systems where global change exerts multiple pressures on buildings and forests, to quantitatively explore the impact of landscape scale forest management regimes on the provisioning of wood for construction, to test the response of the wood construction approaches to current and future climate change and natural disturbances, and to work at the landscape scale of forests rather than in the individual building, which, for this group is probably not that novel, but from an architect's perspective, the idea of looking at a forest is something that's it's not done typically, and is a very kind of odd way to think about things, as we typically think about them as if the world is a limitless reserve of material for us to use. And then finally, to explicitly quantify the wood construction system properties directly related to resilience and management, and climate change driven forest composition change. So where I'm really hoping this is to go, is this study is really only quantifying the Centre de Quebec region, and I think it's really relevant and really important to expand this research across Canada, and as well as other biomes in North America and globally. But that would be the first step. Furthermore, one of the big kind of limitations of this study and my dissertation in general was that many of those wood species that I'm claiming can be utilized have various forest management approaches and kind of limitations from an industrial design application that make them challenging. So kind of understanding the barriers to adoption from both the forestry and wood perspective is something that's really critical. And then essentially to use that knowledge to develop a regionally specific, resilient, and adaptable mass timber, wood construction, or forest bioproducts approaches in collaboration with the communities that they're from across Canada. And then finally, as I said, I'm really interested in working with kind of your group, as well as the wood industry, foresters, and architects to evaluate these barriers to adoption. I was at a conference last week, and I already began discussing with Element 5 some of the issues with utilizing hardwoods in any of their applications, as their main concern is the ability to finger joint things together. So these kind of technical requirements are things that I'd love to get into and discuss further. I have more to say broadly, but I'd love to just open it up into conversation. I'm happy to go through a couple projects, but I think I'd rather just chat for half an hour if that's something that people are interested in.
Perfect. Thank you so much, Peter. So yeah, we'll open up into questions now. So there's a few options. If you want to put a question in the chat, I can read it out for you. Or if you raise your hand, I can go ahead and allow you to unmute, and you can just verbally ask your question. Karen, go ahead and unmute.
Hi there. Yeah, I work for the government of British Columbia, and I've been working on forest carbon and harvested wood products for a long time. And I really love this approach, turning it around and asking who can use the wood, instead of trying to say, well, we want to diversify. What we've done in the past is say we want to diversify, and we consider, different species prices, but not consider changing the downstream demand. So I think that's very cool, the approach you're taking. Something I've long hoped for, and maybe it's wishful thinking, is that we'll have higher utilization and less burning of harvest residues through 3D printing. Because if you just sort of boil it down to like cellulose and lignin and proportions of those, presumably that you should be able to like print a building. And I'm just curious if you're aware of that as a research topic, or any sort of real world applications.
Yeah, so 3D printing is super hot within the construction industry. Typically, we're using concrete right now, but obviously the introduction of wood fiber into that area is something that a lot of research, well, not a lot of research, but some researchers are beginning to explore. One of the big concerns about that from a biogenic standpoint or from a emission standpoint are the glues. So one of the things that was not included in any of these studies is the kind of other products that go into the construction of these different approaches. So I would be curious to know the specifics about the glue composition that would need to be used in a 3D printed wood building. But it's something that's very relevant. And I actually have here, sorry, it's blurring out, but wood fiber insulation, rigid board wood fiber insulation, which is actually soon hopefully to be made in North America. So Timber HP is down in Maine. And they are essentially producing the same product that's been produced in Europe for a while by Styco and Gutex, which is essentially a rigid and a bad insulation that's able to directly substitute out polystyrene insulation or XPS, which is the kind of pink foam that you would typically see. So one of the reasons why that product seems to be successful in the Maine region is because the kind of forest products that they have aren't the highest, so they're not able to necessarily get like lumber out of their forest products industry, but they can get pulp and they can get fiber, and putting fiber into this format versus into this format, which is paper, presumes that we will have a much longer term for it. Where they're really interesting too, sort of longer life cycle for it. So I should be clear. Where I think is really interesting too, from a building perspective, is the just number of species that we can use. So, you could have effectively a very diverse forest, and my understanding, I am not a chemist here, but my understanding is that most of that fiber will be able to be used in these kind of fibrous based, either 3D printed or wood fiber based installations. But yeah, my main concern has always been glues. You look at things like MDF, which from a perspective of formaldehyde and volatile organic compounds has been an issue within the construction industry. So many clients and many standards nowadays are asking us to not have those types of compounds in our buildings. So that's one pressure as well. But yeah, Karen, I know your work really well. I think we spoke maybe 6 months ago or something like that about your Forks model. So I'm really excited to maybe reach out to you and have further conversations about this.
Thanks. Well, we have a few questions in the Q&A here, so I'll just read them out to you. So the first is from Matthew Duvenek. Great to see the expansion of the Mina et al. Simulations explored here in this way. Apologies if I missed something here. Do the mass timber scenarios assume that all wood harvested be used for the mass timber systems?
When you mean by all wood harvested, so essentially the mass timber scenarios assume only the black spruce, or I think I had one extra species here. Sorry, let me go back to the relevant one. So there was 2 scenarios where I looked at the mass timber, so using balsam fir and using black spruce. So black spruce was the kind of one that's regionally appropriate, or has utilized. It exists in Canada as Nordic mass timbers, mass CLT. Balsam fir has been utilized in other regions. I don't know specifically in Canada if it's been utilized right now, but at the time of the study, there were other regions that were using balsam fir. So those are the only 2 species that were utilized in the mass timber scenarios. And then when you look at the utilization for each of them, you're seeing essentially the co-product. So roughly 55%, more or less, of the actual wood product made it through to the building at the end of the day. Does that answer your question, Matthew?
Yeah, thank you, Peter. What I guess so it assumes that all the other species, that nothing else is harvested.
Nothing else. No, it's harvested but not utilized in long-lived wood products, i.e. buildings.
Oh, I see. Okay.
Yeah.
So
essentially the adaptive approach is one which assumes a flexibility in the system, right? So it allows for there to be a CLT diaphragm under some scenarios. It allows there to be, you know, post and beam kind of structure frame, and then, you know, light frame infill, if you understand the kind of concepts that I'm talking about within the construction system. So, you know, there's some more work I think to do on diversifying the different scenarios and being very, very, very specific about them. And that's where we're going with this study.
Great, really interesting work. Thank you.
Thanks,
I'm
Michael.
happy to talk more about it.
Yeah, for sure.
Our next question comes from Clément Hardy. I'm curious to better understand the relation between the numbers that concern the increase in carbon stocked, one of your last slides. If I stock 100% to 300% more carbon in buildings, does that also mean that I harvest 100% to 300% more wood?
No, so that essentially, you're referring to this. So the wood harvesting scenarios were consistent, or they had the same harvest output, depending on each one. It was just the utilization rate. So how much of that wood that was harvested is diverted to a wood building versus non-wood buildings. So essentially by going from a light frame construction, so this approach right here, to the adaptive approach. So if I wasn't as clear, I got a little bit tongue twisted. Under the current approach would increase the wood utilization in buildings, so the amount of wood carbon pool by 105%. Whereas if you were in the extreme climate change scenario and the extreme functional diversification scenario, it would increase it by 295%. So that's the kind of connection between the two of them. So both of them have the same harvest. It's just how much of it is actually able to be utilized in what I'm referring to as long-lived wood products or wood buildings. Primarily because, you know, putting wood into a building is one of the most likely ways for it to stay locked up, for the carbon to stay locked up. Does that make sense, Kamal? I'm assuming he's saying
He
yes.
says yes on the chat. Perfect. Perfect. Okay, one more question so far, and if anyone else has any more questions as we go through this one, you can put your hand up or put it in the Q&A. What is the R value of that wood insulation product? Would it be a viable option for a cold climate like Canada?
Yeah, so the R value of this is the same as the R value, well, it's a little bit less than the R value of the pink foam that you're assuming as a rigid board. So it is totally suitable for a climate in Canada. And we've actually tested it here in Ottawa. So I'm working on a project called Reconstruct for the Hydro-Quebec and the Quebec government, which essentially is a deep energy retrofit project to look at, you know, the 10,000 municipal hockey arenas, kind of generic low-rise residential buildings that exist across Quebec. And we're essentially evaluating the impact of, you know, standard retrofit approaches, which utilize, you know, rock wool insulation, so or, you know, poly-based or oil-based insulation products. And then comparing it to using entirely 100% biogenic assemblies. And we've put it through the ringer here at Carleton, where we have this facility called the Center for Advanced Building Envelope Research, where you're able to put essentially any wall type. You build a mock-up and you put it into a hole in the wall, and they're able to sensor it and test it over a whole year. But then you're also able to use this giant wet wall, which essentially you put it into a large assembly into this wall, and it forces rain, like an abundance of rain at it. And then you can put it through freeze cold cycles. And we've studied it and found that the main concern is mold, because water always gets in. There's no it's the only thing architects can really deal with is water. We have to fight water all the time. And what we were worried about was that the wood fiber insulation would either deteriorate or be, you know, somewhere that mold would build up. And while we found that it did wet and it dried a little slower than rock wool insulation and the standard XPS foam, there was no long-term impacts on resiliency of the wall. Obviously, like, you know, a 20-year study is not possible at this moment, but we haven't found it to be problematic. It's also, you know, pretty tested in Europe. Obviously, they don't have quite as extreme climates as we do in Germany, but they use it pretty prolifically there. And the main reason why I'm personally so excited about it is that it doesn't require retraining of construction workers and kind of redetailing. So there's this capacity to essentially have a building design and then just substitute out almost directly the insulation materials without having to redetail too much, which is really great. There are some additional benefits, such as having a vapor open assembly, and what that means is water and moisture can pass through this, whereas it doesn't typically pass through the XPS foam insulation. And what that means is that when you have a retrofit of a brick panel of a brick wall, for example, I'm going to get a lot of building science detailing here. If you put a panel on the outside and insulate it, you can oftentimes cause the moisture to build up inside that brick, and then the brick will fall apart. So when you use a product like this and you can leave the vapor open, that means the brick can breathe when it inevitably gets wet. So from a maintenance of the existing building stock as well perspective, these wood fiber insulations and these biogenic insulations are really promising. So thanks for your technical question. I could go on for days about that. That's my wheelhouse for sure.
Okay, if anyone else has any questions, now's the time to quickly get them in. But if not, we can finish up for the day. I'll just give a couple more seconds in case anyone wants to raise their hand. Okay, I think we can end it there. Thank you so much again, Peter, for joining us and sharing with us. And just as a final announcement for everyone, this was our, as I mentioned at the beginning, our last webinar of the 2024-25 season. So stay tuned for the fall, or we'll be doing more webinars again. Those are to be determined yet, but we will be in touch as soon as we have that schedule ironed out. So yeah, thank you everyone for joining us for this, and I hope that everyone has a wonderful summer. Yeah, and thanks again, Peter. It was great to have you.
Thanks.